All right, this is your 4.1 lesson. We are starting nuclear chemistry. And we're going to start with isotope recap. So this is what we talked about back in Unit 1. Isotopes are atoms of the same element, but they have a different number of neutrons. Definitely make sure that is highlighted, different number of neutrons. So it's got the same number of protons, different number of neutrons, and because that number of neutrons has now changed, that results in a different in that mass number. Because remember, our protons and our neutrons are what makes up our mass. And because of that, we name our isotopes with the name based on the mass number. So like for an example, we have carbon 12 and there is a one called carbon 14. There is a difference there because of that number of neutrons. Same with uranium 235 and uranium 238. And then just another recap, we have our mass number is equal to our number of protons plus our number of neutrons. And in order to find our number of neutrons, we could take our mass number and minus it from the protons. And remember, in order to find that number of protons is the same as the atomic number.
And just in the upper right-hand corner, reminders about isotope notation. When we write that, you have your chemical symbol. Mass number is in upper left corner, and atomic number or proton number is in the bottom right. I know Ms. Case would always tell you you've got mass number minus protons would get you neutrons. So, you know, these two equations here, when we write an isotope notation, we're kind of able to see that progression and have those two key pieces of information in that notation. And why we are recapping isotopes is because various isotopes of various elements tend to be radioactive and involved in nuclear chemistry, which is our focus in this chapter.
And just real quick, I think Ms. Laporte said bottom right for that atomic number. It is on the bottom.
Or did I really? It is the bottom left. Don't listen to me. Yes, top left and bottom left as well. I almost said right again. Holy moly.
All right, so the atomic nuclei, it's held together by the strong nuclear force. So that's holding those protons and those neutrons together. Okay, this is the strongest force. There's stronger than any electromagnetic force of repulsion. It acts at a very, very small distance, kind of like Velcro. So think about Velcro, whether they're on your shoes, your Trapper Keeper, whatever it might be. And the strength depends on the ratio of neutrons to protons. Okay, that is important. I would highlight that. And then nuclei with 84 or more protons become unstable as they are too big for that strong nuclear force to work.
I love that Ms. Case used Trapper Keeper. Okay. Anyway, the strong nuclear force is stronger than the electromagnetic force of repulsion. So remember, protons are all positively charged. So when you jam a lot of protons, right, 84 protons is a lot of positive charges to have in a small space. And positive charges don't want to be near other positive charges. So even though they are going to repulse or be repulsive to each other, this strong nuclear force can overcome that. But as you start to get way more neutrons than protons, so as that number starts to get more separated, the nucleus becomes very unstable because that strong nuclear force starts to get overwhelmed by the sheer mass of that nucleus. And that's when we get into this idea of instability or radioactivity.
All right. So the radioactivity is the emission of particles and or energy from the nucleus when that strong nuclear force is defeated by the neutron and proton ratio. So that means that the nucleus gets too big, it's becoming unstable, and that process gradually results in more stable isotopes via the nuclear decay process. And we're gonna talk about Marie Curie a little bit later, and we'll do some stuff with that.
So again, key things, notice what's in green there and yellow to be highlighted. Bottom line with radioactivity is the nucleus is just too big. There's too many neutrons compared to the number of protons. And so it can't hold on. It's like if you kept stacking cups and cups and cups or cards and cards and cards really, really tall, the higher they get, the more unstable they get. And that's how nuclei work as well. And what happens then is that the nucleus starts to decay, it starts to break down, and it releases particles. And some of the first people to discover that were the Curies, along with a couple of their colleagues. And we'll focus on their work and the various types of processes and elements that they discovered based on their work with radioactivity.
All right, so we're going to start by talking about alpha decay. This is unstable nuclei, releases 2 protons and 2 neutrons, and that is what that alpha particle is. It's the release of 2 protons and 2 neutrons. The alpha particles are very large, so it can be easily stopped by your skin or a piece of paper. It is the least penetrating type of radiation.
All right, and so let's take a look at what alpha decay looks like. And we are going to just kind of walk through. You saw some instructions there about how alpha decay happens. So an alpha particle, so alpha is 2 protons and 2 neutrons. All right, that's what gets released. And we are starting out here with U-238. Okay, so that is our isotope. So we have 238 on the top. Laporte's got to get out of periodic table. I want to say it's 90 something. Yep, 92 is our atomic number. And as uranium-238 breaks down via alpha decay, it's going to release that alpha particle. And when I have 2 protons and 2 neutrons, that gives me a mass of 4. And if I have 2 protons, my periodic table would tell me that that element is helium. All right, and so an alpha particle is basically just a helium nucleus that is being released from a radioactive substance. But now here's the catch. What do I have left over? So when I release this alpha particle, I don't still have uranium because I just got rid of 2 protons. So my proton number of 92 now becomes 90. And if I look on my periodic table for who that is, I am going to put the chemical symbol for thorium. Now I need to look at my mass, all right? My mass is not going to be still 238 because I just gave away 2 protons and 2 neutrons, or a mass number of 4. So my mass that was 238 is now going to be 234. So when we say alpha decay, this process that we are looking at here is what is occurring. You have an unstable isotope. It is releasing an alpha particle, which basically turns out to be a helium nucleus, 2 protons, 2 neutrons. And then what I have left over is a new element. It may still be radioactive, but it is definitely more stable than its initial radioactive element that we started with, right? And that is an example of alpha decay.
All right, so now we're going to take a look at beta decay. This is the result in a neutron splitting into a proton and an electron. So the proton stays in the nucleus and the electron is released. So that is what we see as a beta particle. Okay, this particle, they're faster and smaller than that alpha particle. So clothing, wood, or aluminum foil are needed in order to stop them. So they're somewhat penetrating.
All right, and let's take a look at an example of beta decay and what that's going to look like. So here we have lead, which is Pb, and its mass number is 214. All right, so we are looking to release a beta particle this time. And from what Ms. Case just said, a beta particle is an electron. All right, we are releasing an electron from our unstable nucleus. So we are starting with a mass number of 214 and an element symbol of Pb for lead. Lead should be 80 something, 82. Testing my memory skills. All right, so we are going to undergo beta decay this time. So the instability in lead-214 is leading it to release a beta particle. And so what happens is a single neutron within the nucleus of this lead is going to split apart. It's going to break up into a positive charge and a negative charge, because we know positive and negative cancels out and becomes neutral. All right, so this neutron splits into a proton and an electron. So what happens is the proton's going to stay. So if I am keeping a proton that wasn't there before, my mass number is going to increase to 83. And if I look on my periodic table, that is going to give me Bi, which is bismuth. Okay, but in terms of my mass number, the proton is just taking the place of this neutron that no longer exists. So we are trading a 1 AMU for a 1 AMU. So my mass number of 214 doesn't change. All right, that is going to stay. All right, so that's what I have left over after I have this radioactive decay of lead-214. But now what did I release? Okay, here's that electron that is what is being released as my beta particle. Well, an electron isn't an atom or an element. It doesn't have a proton number, all right? So we are going to put a little 0 there in terms of its proton number, okay? No, we're not going to put that there, Laporte. We're going to put that here for its mass because it has no mass. But an electron does not have an atomic number. So instead of just putting a 1 there, we're just going to put a little -1. Okay, to remind us that this electron is negatively charged, but there is 1 electron present. Okay, no mass, electrons don't have mass, and we have 1 electron that is leaving us. And as we know, electrons are negatively charged. So this is my beta particle. That is what is leaving. And this is what I have left over after I undergo beta decay. So what we see here with alpha and beta decay are 2 different particles, 2 different radiation particles that are released that can cause some changes in various structures depending on the levels at which those alpha and beta particles get released into the environment.
All right, so let's take a look at gamma decay. It is when there is a release of high energy and electromagnetic radiation. Okay, so this is pure energy. Those are your gamma rays. They have no mass and no charge, and it travels at the speed of light. It usually is released with alpha or beta particles, and the nucleus remains the same following the release. So gamma rays are the fastest and the smallest of all the radiation types. So lead and concrete are needed in order to stop them, and they are the most penetrating.
So gamma rays are usually the ones in all the superhero comics that cause superpowers to occur. That's not a real thing, by the way. But if it were, gamma rays would be the ones they are usually using. And you can see that is because it is so tiny. It is really electromagnetic radiation. So this is high energy. Look at your bulky alpha particle, even compared to gamma rays, your bulky beta particle. Gamma radiation is extremely strong and can penetrate and damage our DNA, much like its kind of cohort or counterpart, which would be X-rays. They just tend to be a little less damaging than gamma radiation does. And those are your 3 different types of nuclear decay. So when we say something is radioactive, what we mean is that it is releasing either alpha, beta particles, or it is releasing gamma radiation.